So where were we? So we discussed regular polygons last time. We discussed the 3 regular tilings last time. We gave them names. Do you remember? The tiling with the hexagons, like a honeycomb, that was called 666. The tiling with the squares, like the regular thing that you see on every floor almost, floor tiling, is 4444. And then there's the tiling with equilateral triangles, and that was the one that has 6 triangles surrounding each vertex. So it was 3, 3, 3, 3, 3, 3. And that's cool, Madeline. It's all right. Do what you got to do. So today we're going to take it from there a step further. We're going to use that naming system to learn about the tilings that are just slightly more complicated than the regular tilings, namely the semi-regular tilings. Now, that's not the end of the story as far as tilings go. There are such things, for instance, as demi-regular tilings, and I'll mention those when the time comes. But they're not, you know. Once you get the idea, once you get the naming convention down and everything like that, it's a natural step. Right? We're going to stop at the semi-regular ones. One of the reasons why we're going to stop there is just there are very limited amounts of those. We had 3 regular tilings, and it turns out that there are only 8 semi-regular ones. So altogether, we're learning about 11 different tilings that you can make with regular polygons. All right, does anyone have a question about what a regular polygon is? They're okay with that? So it's the kind of polygon where you have equal sides and equal vertex angles. Okay, so Lasers here. Hey, so let's see. I actually posted something on our Blackboard page, and I want to take a look at that. So we'll just kind of approach this from a from the answer, basically, because you might say, well, you're telling us that there are 8 semi-regular tilings. I wonder what they are. In the book, they go through the whole construction. You know, here's the kind of things that could fit together. Here's how we could possibly make that happen. And then you look at various options. You know, if you have this kind of setup around one vertex, could it extend to a tiling? And I do want to do some of that, but lucky for us, we don't necessarily have to, and I will not require you to know all these various rules like they have in this section 4.1. Like they have, for instance, rules like this. Let's see. No semi-regular tiling can have vertex configuration K and M, where K is odd and N is not equal to M. Okay, so if you read through the chapter and you're interested, and it does make total absolute sense when you're doing it, when you're going through it line by line, but you don't have to. I'm not going to ask you to use these kinds of rules. But it does make good sense, you know, if anyone's interested. Oh, before I show you the 8 semi-regular tilings, were there any questions about the homework I assigned? I assume there's something. Anybody?
We didn't have to submit it anywhere, did we?
That's correct. That's correct.
Okay, good. Just making sure.
Submit. Yeah, I'm expecting only some questions, but nothing to turn in to have, you know, be submitted. Well, one of the things that I asked you to do was to look at the vertex angles in exercise 2 on page 86. And that's kind of the basis of how we start fitting these things together. Okay, so and I ask you to do number 3 as well. Largest number of regular polygons that can fit around a vertex. Okay, so let me get you started with exercise 2, and then we don't have to spend a whole lot of time on that stuff, but let's look at that a little bit. So this here is a table, and this is problem 2 on page 86. And here we have, and this would be number of sides. Oh, let's just do it like this. Vertex. We could simplify this a little bit. So polygon, more importantly, I want to know what the n is, right? So if we have a triangle, for instance, n-sided, the vertex angle, this I should mark here. This is these. We're only talking regular polygons now. If you have a triangle, and you know the polygon is regular, then we can use this formula that we did. We derived that last time, if you remember. That's where you have 180 times n minus 2 over n. This is the formula that we're using for each of these. So if you stick in a 3 in place of n, what you get is 180 times 1, because 3 minus 2 is 1, divided by 3. So 180 divided by 3. And that, my friends, is 60. It's always been 60. And it always will be. Now, again, this only applies for regular polygons where you know that the vertex angles are the same. If they were different, then we couldn't possibly give it a single value, right? So if n is 4, the vertex angle would be 180 times 2, 4 minus 2, divided by n. So that's 180 times 2, so that's 360 divided by 4. That's 90. So in this fashion, in problem number 2, you're supposed to go through quite a bit of these options for polygons. For hexagon, you have n is 6, and it turns out that angle comes out to 120, which makes sense actually. Remember the polygons that we had? I mean the hexagons. So here's an example. If you have regular hexagon, whoops, this is a horrible example of a regular hexagon. Okay. Please don't quote me on this. Okay. This might be the if you knew any bees and you'd show this to them, they'd be like, I'm not living in that hole. All right, so this here is this guy here in the middle is a vertex, and around that vertex you've got 3 hexagons, 3 regular hexagons. Now, doesn't this make sense after calculating that the vertex angle of a regular hexagon is 120. So you have 3 of those, each 120, 3 of those coming out to 360. Makes good sense. All right, so this table that you're supposed to fill out is a great resource when you're starting to put these polygons together, and especially when you have various types. Like for instance, and this is something I did a little bit with you guys. Was it last time or time before? We did some work on this tessellation creator. Okay, I'm gonna switch to this. Actually, you know what? I'll do one more. Sorry for bouncing around, but I'll skip a couple here, and I'm just gonna illustrate how you would go if you were gonna do a thorough job at this. Let's say 10 here. If you do a 10, 180 times 8 over 10, what does that come out to? 180 times 10 minus 2, so that's 8, 180 times 8, and then divided by 10, it's 144. So I'm just going to illustrate, so let's keep this in mind. And I am going to show you how you could go through some examples and check them. So you can use this kind of technology to check. For some reason, that's not loading completely. There we go. So I'm just going to illustrate. So if we had a 10-sided thing, now remember the 10-sided regular decagon had a vertex angle of 144 that we just calculated. And I'm going to put with it a fiver, a regular pentagon, and another one. And notice, oops, notice that they actually work out here in one vertex, like so. So this is what you would call, this vertex here is what you would call 5, 5, 10, because you've got a 5-sided polygon, 5-sided polygon, and then a 10-sided polygon. So that vertex is a 5, 5, 10. Now, the fact that these 3 can be put together around a vertex, what that means is that's a candidate for what's called a semi-regular tiling, meaning that this idea of putting 2 pentagons, regular pentagons, and a regular decagon might extend out to a tiling where you're using more than one type of regular polygon. That's the difference between regular tiling and semi-regular tiling. Is in regular tiling, we were using just one type of regular polygon, and in semi-regular tilings, we're using multiple types. So here you have 2 types. You have the regular pentagon and the regular decagon, 5-sided, 10-sided. All right, so would this work in the long run? Like, can we actually make a tiling out of this? I can see that I could stick a 5 here, almost like a flower and its petals like this, right? It actually looks pretty much like a flower and its petals. And so it's promising. This is all looking pretty good. So I'm going to keep going here. I know my friends in the Moomin Valley are hopeful. They're always optimistic. They're hopeful that things will work out. Okay, so pretty good so far. So promising. So this is almost like a flower with the 10-sided regular polygon in the middle, and then you have these 5-sided regular polygons, so regular pentagons as the petals. So good start so far. Now, will this extend? So what we have to do is we have to see if I can make all the vertices the same. If I can have a 5, 5, 10 at each vertex, okay? So I'm going to stick another 10-sided polygon there. And so that makes this vertex here 5, 5, 10, okay? Now, can I make this vertex 5, 5, 10? It's not going to happen, is it? See how there's going to be an overlap of the decagons? So this here is the kiss of death for this particular tiling attempt. So 5, 5, 10 is not going to be one of our semi-regular tilings. So if you read this section in the book, they explain some reasons for why that wouldn't work. Now, we could make a cool looking tiling out of these guys, so maybe we'll just kind of skip one, right? And then you could fit some different, you could possibly fit some different polygons in there. But 5, 5, 10, as written, is not going to work because each vertex would have to be identical, okay? So let me just now define semi-regular tiling for you. A semi-regular tiling, although I defined it in words already, but I'll do it in writing as well. Semi-regular tiling is an edge-to-edge tiling made up of more than one regular polygon. And an additional condition has to be met. Moreover, each vertex has the same configuration. See, with the regular tilings, we didn't have to worry about that because we're only doing one type of polygon, so that wasn't an issue. But here, with semi-regular tilings, that is an issue because we want to make sure that each vertex has the same exact. They have to be identical configurations. So if 5, 10 was going to work, every single vertex would have to be 5, 5, 10. Now, if you make up a tiling using more than one regular polygon and it tiles the plane, but this last condition is not met, then that's when we would have what's called a demi-regular with the D. Demi-regular, like Demi, who's that singer? I know there's Demi Moore, but then there's also Demi Lovato. Demi Lovato. All right, so Demi, I don't know if she was named after demi-regular tilings or demigods, or I don't know what she was named after. Or maybe she was named after Demi Moore. Actually, I'm saying that wrong. Do you guys know this? This is just for your civic education. It's Demi Lovato, but it's Demi Moore. Did you know that? Both are D-E-M-I, but Demi Moore is the actress that's a little older than Demi Lovato, or a little less young, just to stay on the PC side of things. Can't say older anymore. I'm not sure if that's true, but I'm just assuming. So I digress. But anyway, demi-regular tilings would not have the same condition here at the end. You could make demi-regular tilings all day long, all kinds of different ones. There's basically unlimited ones. And if you Google that, you'll get hundreds and hundreds of examples of demi-regular tilings. However, I don't want to blow that up. I don't want to get too crazy with this. So we're going to just focus on these semi-regular tilings. So this is where we stop with this stuff. So semi-regular tiling. So what are some examples? Now, like I said at the beginning, I'm not going to go through the whole thing. I'm just going to show you from Blackboard what I already posted. And we could basically start from here. And then we'll play with the tessellation creator just to remake some of these. So I'm going to now share my Blackboard page. And so this is already something that's posted. And, oh, whoops, looks like I have a wrong date there. There's, and at the bottom it says for Tuesday, 9/29. That is not correct. There will be a project like that, but next Tuesday is not 9/29. It's going to be more like 2/23. Anyway, here you have the pictures of 8 semi-regular tilings. Now, the first one looks pretty familiar. This is the kind of tiling you might see a lot in houses like built in the 20s, 30s, 40s, 50s, especially in the bathrooms. This is a very commonplace tiling. It's called 488. Let me just create it with you. I'll recreate it. And, oh, oops. And then hopefully you'll remember how that works. So 488. Okay, so I usually like to start with the bigger or the biggest one, especially if I'm drawing by hand. It's easier to draw the little ones attached to the bigger one than the other way around. So 488 would mean that each vertex has a square and then 2 of the regular octagons. 488. Okay, so I'm going. By the way, you'll see one thing is very consistent. We always start with the lowest number, smallest number. So if I have 4s and I have 8s, I'm always going to start with the 4. So the name, that's part of the naming convention. Start with the smallest possible number. 488 in this case. So around one vertex, around each vertex, there's a 4-sided thing, and then 8-sided, and then another 8-sided. So 488. So then notice this has a real nice, harmonious feel to it, and real familiar feel. It's very well. It's about as square as they come, as far as the semi-regular tilings. It's not a tiling by squares, but it's pretty bland, but a little more complicated than the 4444. You see how this works? You've seen this before, right? So 488, standard stuff. It would be a little more expensive to make than the 4444 because you'd have to have 2 different types of tiles, and especially the octagonal tiles might be a little more expensive to cut. But this is nothing too crazy. Okay, so we have 488 like that. Now, let me go back. So I'm going to go back and forth a little bit here and look at the various tilings. So 488, I just showed you an example of that, how to make it. 3636. Now this is, you don't see this as often, Notice the top row, the middle one is called 3636. So let me see if I can make that real quick. 3636. So like I said, I usually start drawing with the bigger one. Make that red. So each vertex is going to have a triangle, hexagon, triangle, hexagon. By the way, you're more than welcome to join me in creating these things. So this is the tessellation creator that I posted on Blackboard a while ago. And it's free to use. You're encouraged to mess around with it. And with this tiling, it's actually it's a little bit easier to mess this one up. Just because sometimes what happens is you accidentally create a tiling that turns out not to be semi-regular, although you're using the same exact parts. You're using equal amounts of triangles and hexagons, but if you look at each vertex, sometimes, actually, let me show you how you could mess this up, because it's a very common mistake. It's worth showing. Some mistakes are good to get into. So I'm gonna wipe these out, okay? So you know what the tiling is supposed to look like. And so what happens a lot is people do this. So it looks similar, and it looks like it'd be okay, but notice how this vertex here is 3366. This one's also 3366. Whereas these ones, what I was doing earlier, are 3636. And so if you remember, the second condition on the semi-regular tilings is that every vertex has to be the same. So this would not be a semi-regular tiling. It does work. It does tile the plane, but it's just not semi-regular. It would be the demi-regular type. So let's put it back to where it's supposed to be, like this. You can remember it by having a regular hexagon in the middle, and then like this kind of star, the David star, with the equilateral triangles. That's a good starting point for this kind of tiling. So that's pretty cool like that. This is a real neat tiling, and definitely more expensive than the regular ones, or especially the 4444, and then another popular regular one is the 666. But in any case, this is a real nice tiling, and sometimes you'll run into it. Not in the U.S. so much, but sometimes traveling in other countries, you might see it. For instance, I've traveled some in Southern Europe and then Turkey, for instance. And in Turkey, you see a lot of very cool tilings, just in ordinary buildings, floors, walls, whatever. So this kind of tiling wouldn't be even that special over there. Alrighty. Any questions about 3636? Okay. Let's move on to the next thing. I don't know if I'm going to go through every single one, but just to show you that these really can all be done, and they all fit together. Maybe in this next one we'll do a little bit of math just to kind of verify that the angles work out. The angles for the set of polygons that are meeting at a vertex, those vertex angles will always have to add up to 360. So I'm going to now draw 3, 4, 6, 4. Notice that this one has 3 different kinds of polygons meeting at a vertex. Is this making sense to you guys?
Yeah.
3, 4, 6, 4. Yeah. So this is a nicer way to approach it rather than going through those rules. You know, K and M doesn't work until K is odd and N has to equal M. Like that's all well and good if you're into that, but I'm just showing this to you this way because I think it's this could be a very visual and nice topic. So 3, 4, 6, 4. So what that means is I'm going to have squares attached to each of the vertices, each of the edges of the hexagon, and then the triangles will slide it right into the middle, in between. So let's see. It takes a little while to get comfortable with the tessellation creator, but it does work quite well. It's intuitive. Okay, so then I'll put these in between. So I'm making 3, 4, 6, 4. I'm making sure that every vertex has triangle, square, hexagon, square. 3, 4, 6, 4. Okay, 3, 4, 6, 4 for every vertex. Now, what do we do next? Where do we go after this? So let's put a hexagon. I know because I've done it a few times. 3, 4. That does not go there. This would attach to the square. So 3, 4, 6, 4, like this. Okay, this should work. 3, 4, 6. So this vertex is 3, 4, 6, 4 as it should be. And in fact, now I can just attach these squares like that. Yeah, you guys should be doing this, not me, but I'm just going to show you. Ultimately, you're going to make some semi-regular tilings for your project, but not for Thursday. I'll give you more time than that. Okay, so here we have the beginnings of the 3, 4, 6, 4 tiling. I'll just leave it at that. And 3, 4, 6, 4. That's what that looks like. And maybe we'll look at one more. That should do it. That should make my point. Whoops, I went to the wrong place. Again, this set of 8 semi-regular tilings is already posted on Blackboard, so you're welcome to it. Whatever homework I'm giving you for Thursday, you don't have to turn in, and the scans, I'm still doing the scans. I'm going to stop doing it pretty soon. Does anyone not have a book at this point? Do you guys need the scans? Because if you don't, then
I need scans, Professor. I still do.
I still do as well.
All right. Okay. So I'll keep doing this for now. All right. So here we have 3, 3, 3, 3, 6. 3, 3, 3, 3, 6. Wow. So what that's saying is, oh, I forgot to do the math for the 3, 4, 6, 4. Maybe we'll just do it here. So each vertex has 4 triangles and then a hexagon. So each triangle contributes 60 degrees, right? 60. So if I have 4 of them, that's 240. And then the hexagon rounds it out. The hexagon was 120. So 240 plus 120 is 360. So that's why that works. If I go back to the 3, 4, 6, 4, in fact, let me do a whiteboard here with the 3, 4, 6, 4. We have the triangle contributing 60. The square is contributing 90. The hexagon is contributing 120. And then finally we have another square. So what does that come out to? 60 plus 90 plus 120 plus 90. I mean, it better come out to 360, right? But you could check. The 90 and 90 together are 180. And then it's easy to add the 120 to that. That comes out to 300. And then you have the 60 from the triangle. So, yep. So 360. And so that, you know, I might ask you to, on a test or something, I might ask, you know, what is the sum of the vertex angles for this group of regular polygons? Something like that. So for, you know, any candidate, let alone actual semi-regular tilings, but any candidate for a semi-regular tiling, the vertex angles would have to add up to 360. So let's go back to this for a little bit more. So we have the 3, 3, 3, 3, 6. We have the 4, 6, 12. The 12 is the largest number of sides we're going to have in these tilings. And that comes up twice. It comes up in the 4, 6, 12, and it comes up in the 3, 12, 12. The 3, 12, 12 is really, really cool. It's kind of like the 4, 8, 8, but with just more sides and the big one. So they look a little more circular, and it would be a lot harder to cut. You know, if you're thinking about cutting tiles by hand, for instance, like they used to, the 12-sided to make it even, to make it symmetric, to make it actual regular polygon, very hard to do. So you don't see so many of those. Not with the CDC computer cutters. I'm sure it's a lot easier to do, but people don't really want to. People don't usually want to pay the extra money to get a 12-sided polygon as opposed to 8, but some do. Okay, now the bottom row, these are interesting. They're interesting because not so much so because, you know, you have just triangles, squares. That's not the interesting part. But the interesting part is that they both have 3 triangles and 2 squares, right? 3 triangles, 2 squares. It's just that they're in different order. The 3, 3, 3, 4, 4 looks so much straighter. You know, look at that row of squares. Just, you know, just creates this big line, thick line in the middle, and then the triangles are like a zigzag in between those lines. Totally, you know, unique mood to that tiling. When you look at these other ones, they don't really have lines like that. Not thick lines like that. But the 3, 3, 4, 3, 4, notice you just swap the third and fourth polygons in that classification, 33434 looks almost chaotic. It looks like it's like it's got some dimension to it, like it's kind of bulging out. It's got a little concave, convex thing going on, or something. That's certainly a lot more interesting than its sibling here, 33344. So 33434, you rarely see out and about. I remember sometimes I've asked students to take pictures, or actually, I remember before the cell phone cameras were so popular, I remember asking for a list from students. Give me 5 tilings that you've seen lately, or between, let's say, a Thursday class and a Tuesday class. And some people would list these, 33434s and 31212. Like, oh, where did you see that? Because I know for a fact that they didn't see it. I mean, maybe in a book, but the whole exercise was to just keep your eyes open, what you might see out, in a sidewalk, or a kitchen backsplash, or bathroom tile, or something like that. And that, if anybody says that they see a 33434 on their daily route, then they're probably lying. Has anyone seen a tiling like this? Does this ring a bell?
I actually recognize that one from Photoshop. There's a certain like puppeteer like mesh. I forget what it's called, but you can like stretch things out, and this grid shows up for it.
Cool. Yeah. No, that's definitely yeah. See, it's cheap to make stuff like this, in the digital world.
Yeah.
If you know what you're doing, it doesn't cost any extra money. Out there in the real world, the real tile, stuff that people had to make by hand, or now with machines, it's much more complicated and expensive to make some of these more involved tilings, like a 3464. You rarely see that, but it can be made, and it has been made, but it's just not very popular around these parts. In the part of the world where the Islam was popular back in the day, it's popular still in many of these places. But you would see a lot more interesting tiles and tilings, and we can get into that a little bit next time, and we will. So these are the 8 semi-regular tilings. Just note that, like the one I started with, the 5, 5, 10, just because 5 and 5 and 10 fit around one vertex, it doesn't necessarily mean that it's going to extend to a tiling. And that's why I wanted to start with like a non-example, because I wanted you to see that it doesn't, just because the vertex angles add up to 360, it doesn't necessarily mean that that combination is going to work out. The 558 was 108 plus 108 plus 144. That comes out to 360, but it just doesn't work out. Then it turns out that there are 17 candidates, of which 11 work out. So 5, 5, 10 is one of those 6 that don't work out. So you can read the book for more info on that. Now, in fact, I even say that here. There are 17 combinations that add up to 360. Of those 7, 11 extend out to tilings of the plane. Now, next up, what I want to do is show you something, kind of a natural next step. And for this, I'm going to draw some, let's see. I'm going to try to draw 3, 6, 3, 6. Give it my best shot. Just freehand. So bear with me here. It's already looking not so good, but let's see. Okay, so each vertex is going to have a triangle, hexagon, triangle, hexagon, right? The goal is to make all the edges the same length, and especially if you're doing freehand, it's hard. But I encourage everybody to practice this in various ways. Okay, so and the next thing I'm going to teach you is, I'll tell you about, is this idea of the dual tiling. So the way that the dual tiling works, and by the way, I'll just put here 3, 6, 3, 6, 3, 6, 3, 6, just a pretty horrendous looking version of it, but anyway. The way you do the dual is by marking the midpoints, the center of mass, or just think of it as center of a group of these regular polygons. Just marking the centers here. I'm going to mark them all since I don't have that many. So the dual tiling procedure is you start with, I'll write it here. 1, mark the centers of the tiles. And then 2, connect centers of tiles that I'll put of any pair of tiles that share an edge. Okay, so we have to unpack that a little bit. Connect the centers of any pair of tiles that share an edge. Now let's talk about that. For instance, look at this hexagon here. Which tiles does it share an edge with? All of these triangles, right? This one, this one, this one, and this one. It does not share an edge with any of the other hexagons, right? So I'm going to connect the center of the hexagon to the centers of the triangles that are around it, because these are the tiles that this hexagon shares an edge with. Now, if I had drawn more triangles around it, you'll notice that it's going to have 6 lines coming out of it. And similarly, the triangles will have 3 lines coming out of them, if you complete the picture. So however many sides the thing has, that's how many lines it's going to have coming out of it. So I'm drawing the dual to 3, 6, 3, 6 by connecting the centers of any pair of tiles that share an edge. That's the guideline. Now, if I had more, I would get kind of a familiar picture, actually. I think that you would recognize where this goes. It's like you get these quadrilaterals that make up this this pattern. That it looks kind of like cubes. It looks very three-dimensional. Did you notice, by the way, that I put this picture on the home page? So this would be a really cool way to make a 666 tiling interesting. Notice that the tiles themselves are just hexagons, but they've made them interesting by adding those lines. It's kind of like a Mercedes-Benz sign in each of these hexagons. But what that's doing is it's basically making the dual for 3636, and it looks immediately more interesting and more lively, and it's got a real 3D quality to it, because they makes it looks like some kind of convex cubes, convex or concave, depending how you see it. Anyway, so that's the idea of the dual tile, and I'll do another one. Let's see, maybe I can pull up just real quick. I'll pull up, let's say, 3464 tiling. Pull up a picture of that, and then just draw the dual on top of that. These have pretty wild names sometimes, like the 3464 tiling is called the rhombi trihexagonal tiling. Okay, the rhombi trihexagonal tiling. And let me try to find a picture that's only got one color, because that would be, I would prefer that. Okay, this is pretty good. Okay, so 3464. Okay, so here's 3464, and not the best resolution, but that's okay. We don't need to get too fancy here. I'm going to mark the centers of a bunch of these edges, or a bunch of these tiles. Okay. Technically, you don't even have to do this step. If you know what you're doing, you can just start connecting the centers. You can just kind of eyeball it, but it is easier to eyeball these things if you mark the centers. Maybe I can start here. Maybe I'll get the hang of it, and then I can just make the lines. So can somebody help me out here, since we can all draw on this? So could somebody connect some of these lines with the red, connect some of these centers with the red line? So you can click on the shapes thingy. Yes, yes, yes. And then that's it. Yeah, yeah. I forgot one center there in the triangle, in the dark triangle there. Oh, wait. All right, I'm not going to ask who that was, but that was not the. These connections here are not correct. Okay, so the center of the triangle will not be connected to the center of the hexagon because they simply don't share an edge, right? They share a vertex. They have a vertex in common, but they don't have an edge in common. So this line between this triangle and hexagon, and then this line in the same situation. And somebody started here, I think. So let me go ahead and wipe this out, and let's try this again. Maybe you could do it without the centers, if you're comfortable. And don't worry about messing it up. This is where we practice. So see if you could just connect the centers of those tiles that share an edge. So basically what you're doing is you're connecting the hexagons to the squares, and then you're connecting the triangles to the squares. Yes. Now that is looking good. So you're creating the dual to 3, 4, 6, 4. So who's red and who's blue here?
I'm doing the red right now.
And who is I? Oh, Madeline.
Yeah.
Madeline is doing the red, and who's Mateos? Are you doing blue?
I'm doing blue, yeah.
Excellent. Someone else could do. There's plenty of room in the bottom. You could even pick a different color. There's plenty of real estate. Anyway, so this is good practice. You can find the 8 semi-regular tilings, so many different places online, and you can just put it on your Photoshop or whatever program you like to use, and just practice making these dual tilings. I'm going to ask you to turn one in, not for Thursday, but for next Tuesday. So this is great. Who's orange and who's purple? Because I actually can't tell.
Fiona's orange.
Where I'm sitting. Fiona is orange, and purple is Sanaya.
Yeah.
Is that right?
Yeah,
Excellent.
I'm doing purple.
Cool. All right. So this is great. So this is the idea of the dual tiling, and I'm going to give you a couple of exercises for Thursday, where you'll do a little bit of figuring this stuff out. And I've already posted the homework on Blackboard, so it will be to work out exercise 18 on page 91, and then exercise 21 on page 92. So 91 and 92 are about the dual tiling. So, you're welcome to read this whole section 4.1 and think about the different kinds of rules that they mentioned there, and some of the stuff is proved. I didn't go through all those constructions because to me this is an extremely visual topic. So I prefer to really just get into that applet and put some polygons together and see if we can.
Professor, you'll
see if we
upload
can,
the scans, right?
Just see it. Yes, I've already done that. So page 91 and page 92 have been uploaded, and the couple of homework problems that I would like for you to look at are mentioned in the Blackboard, so 18 and 21. And
Perfect, thank you.
that is, you're more than welcome. So that is what I have for you. And before before I go, thank you, by the way, for helping me out with the dual timings. It's kind of fun when you get into it. So I wanted to tell you about a couple of these characters real quickly. So this guy his name is Haizuli. So it's Stinky. And this is my favorite. His name is Nuuska Muikkunen, and he's a musician. He's a traveler. And this guy is a real woodshed specialist. He'll build you anything out of wood, furniture, boats, whatever. And yeah, see, the movements have been around since like the 30s, almost 100 years. And it was this awesome character named Tove Jansson, who drew these, and unbelievable. She lived on an island by herself. So she would have to take the boat, for any groceries, and she would just fish and stuff. And she wrote these books, amazing books, and designed all these characters. So yeah, if you have a chance, look at the movements, and I think you'll be glad you did. They're kind of deep stories. There's something for kids, and there's plenty for adults too. Alrighty, so that's it for today. I hope you enjoyed it. Semi-regular tilings. Next time we're going to go on to talk about MC Escher, and you're going to see how MC Escher used these kinds of tilings in pulling off some of the magic that he did. That's why we're doing this, and also just because it's good to know about. And when next time you walk on the sidewalk, you might notice, oh, that's a 666. I didn't even think about that. Anyway, talk to you later.
Bye.
Bye.
Thank you.
Thank you.